I'm Regina Chan. I'm Vice President at Goldman Sachs, primarily working on an internal data lake. And so what we did was actually build this data lake from the ground up. And what's actually unique about us, right, is that we have about 700 terabytes of data, 90,000 data sets, and we have a lot of data of all different shapes, sizes, and velocity. So it's all sorts of different things. On a daily basis, we process 7 trillion records a day, and we have about a 40% growth year over year. And so when we're talking about scale, that's kind of what we mean. And so with that, I'm really here to talk about how we use Flink and how we do it at scale. So with that, we want to set the stage a little bit to kind of go back to where we were before, right? So if you look at the traditional data warehousing model, right, you have your databases, and then you have custom ETLs going into a specific data warehouse of choice, right? So with each new database comes a new dedicated ETL, and then dumping into a warehouse somewhere, right? So technology for the warehouse is typically fixed, and so along came a lot more data, that being from log data, from all different other sources of data. And so when the data fills up beyond the warehouse, right, do we have to re-engineer these ETL pipelines? Do we think about something different? So the idea of putting the lake data into a central place really was born, right? So with that, you might see a lot of the word data lake, right? Everybody likes to have a data lake. Everybody likes having data in a central place. You might see these databases having some sort of Lambda process, dumping data into, say, S3, and then using something like Athena to query against it or to push that data into Redshift. So this at scale, when you're talking about 90,000 data sets, right, this becomes kind of hard because what are you using to really manage each of the different data sets? How do you manage each of those pipelines? Now, Amazon has kind of recognized that building data lakes is hard, right? So they've really come up with Glue and lake formation, right? So Glue gets you kind of out-of-the-box ETLs, with some sort of discovery of your table definitions and schema. And then your lake formation kind of gets you a catalog where you can have a view of all these things, and then has a concept of entitlements built on top of it, right? So with this, what we don't solve is actually what happens when we have not something that is static, where we're pulling data from some place and dumping in there and letting it be to be queried, and we have something a little bit more dynamic, right? We have incoming data all the time, and the data continues to get updated. So the other questions around this is basically around how do we discover kind of information about the data around governance, around lineage, and also how do we make sure that data is actually reproducible, right? So with that, we kind of took a look around and defined a set of principles for what we wanted in a data lake. So for one thing, if we wanted anything to scale, we wanted nothing to be hard-coded in any particular way. We really wanted dynamic pipelines. So everything should be metadata-driven. What we also wanted was basically the ability to decouple producers and consumers, and we do that in 4 different ways, right? We do it temporally, meaning producers can put in data before there's even consumers for it. They're not tied at all in time. They can be on completely different technical stacks. So a producer can be using Kafka or a database of choice, and then consumers can decide whatever they need to choose. Operationally, so the contract for producers and consumers is with the lake itself, and so therefore any issues with the producer side of the problem gets contained within producers. Any consumer-related problems get contained within the consumer side, and all of them interact with the lake at the center. Locality is actually another interesting thing. As the cloud strategies continue to expand, right? There's many, many different cloud providers between AWS, GCP, Azure. And the reality is that as a bank, as Goldman Sachs, there will be multiple use cases for each of the different cloud providers. And so if we were to say the lake only exists in AWS, the lake only exists in GCP, then we have a cloud provider lock-in. And so instead of asking, how can we use technology to solve the problem, you're really deciding the technology ahead of time and saying, this is the answer, right? So what we see is really using the lake to be kind of a bridge between the different cloud platforms. The data can be sitting in all different sorts of places, and the idea is for us to be able to service the data there in the respective cloud platforms. So 3, I touched on a little bit. We want to make sure it's technology agnostic, not only on the producer and consumer side, but we want to be technology agnostic internally as a stack. So any changes that we make internally should be transparent to our users, being producers or consumers. The reality is that we live in a world with lots of regulatory requirements. So a typical platform lifespan is about 10 years. So the reality is that technology will continue to change. And so we want to be able to have a flexible enough architecture that allows for that to happen. So number 4 comes into shared infra management, right? What we mean by that is that rather than having many, many copies of the same exact data, what we do is that we have shared instances of databases that people can actually query on. So you get shared usage of the actual databases. And then in addition to that, when people run their jobs on, say, a Hadoop cluster, rather than having their own, we actually have a multi-tenant Hadoop cluster, which we then can run on our cluster. Now, obviously, there's use cases for people to bring their own database or bring their own cluster. But for the most part, this covers the 90% use case. Number 5 comes around what we mean by reproducibility, and we want audit-level reproducibility. So when, say, the feds come back to us saying, how did you get this particular number on this report, say, 2 years ago, we have the exact code version, the exact data that we used to run that report. And similarly, if there was a bug in that code and we need to regenerate the data, we can fix the code and then rerun the exact data and generate new numbers. And then also discover what happens there afterwards. What are the downstream dependencies that would have needed to change their data as well. So in addition to that, we want to handle replication for firm having backups of the data. Even if we lost a complete data center, we still have the ability to recover and actually have no data lossage. Lastly, being the bank, of course, we want centralized controls. So basically, we have a lot of data that is PII and sensitive in all different sorts of manners. So it really means having table and row level entitlements, in addition to the fact that there's a lot of different granularities that we need to define controls around. We have as many as 100,000 groups across our datasets. So that's kind of what we defined. And because a picture is worth 1,000 words, I just want to take you through what the architecture really looks like. So we have producer flows where they come in and register their data sets into our registry service over here. Within that, they define their schemas, they define where the source is, they define what schedule to run at. They can trigger us as well. At that point, we will schedule jobs in our ingest service and actually pull the data from source. And then we put that into staging, which we then use to validate. And then we do something called merge, which is where our main milestoning algorithm happens. After all that, this gets committed into the Lake store, and then that's where consumers really come in to define a virtual warehouse to say, I need to read these specific data sets. And they will tell us here what the technology of choice is, right? So we have IQ, ASC, DB2, MemSQL, Elasticsearch. And the idea is that as these technologies continue to change, they're kind of a connector approach, then we can just kind of expand out our what virtual warehouses we support, right? Within there, we also have this line coming out here, which represents transformations that the consumers actually make. So we call these refinement service, which is basically taking the sets of data sets that they read inside the warehouse and then doing some transformations, thereby generating new data sets that we then stage. So inside here, we originally had a kind of each of these stages were represented by different jobs. Internally, we used a technology to kind of pull this data. We had a Spark job that represented the validation. And in validation, actually has the native kind of default validation that we do based off the schema, looking for data that's bigger than the schemas that's defined. And things like trailing spaces and the merge we originally implemented back using Spark. Now, we changed the main merge algo and re-implemented that using MapReduce. We saw about 100x performance increase. What we then did with Flink in a little bit 2 years after that is actually combine all these into one single job. Right? So Flink can then act as our ingest service, as well as to be able to run that validation and run the main milestone algorithm. And what this did was actually reduce some of the latency in between these jobs, and then just make it a little bit more efficient in terms of serialization across the data coming across. So with that, I wanted to really talk about how we dynamically generate these jobs, right? So in order to even dynamically generate these jobs, we really have to read the metadata, right? So we have the ingestion types, meaning what types of sources comes from. The batch type, is it an incremental or a snapshot or some sort of delta feed? We have the milestone type, meaning do we do default lake milestoning? Is it unitemporally defined? Is it bitemporal or some other type like that? Is it partitioned or non-partitioned? What file output type do we write? Do we use Parquet? Do we use Avro? And then do we have a multi or a single dataset transaction type, meaning do all the datasets commit together or are they individually independent and commit each dataset at a time? And then obviously the processing state. Where is it at in its own processing state and where do we need to pick up from? So what we do is that we actually translate each stage and the combination of these metadata attributes into one or more operators. Going this way. So going from here, if you look at the job graph, it looks like the ingest side is represented by a data source. People can also push the data to us, but the idea is that we read the data from somewhere. And then what we do is that, oops. Okay, so then we validate the data as either defined by the contract or by the default validations that we run. What we then do is actually have a data synced, writing out the staging data coming out of here. And then the red here represents our main milestoning algorithm, right? So what we're doing is that we're extracting the keys coming out of the staging data, as well as reading the data from the previous batches that we had, and then extracting those keys out, and then moving this into a code group operation where we perform our main milestoning algorithm. And then we also calculate checksums that we then use for comparison in our kind of delta-based replication. And then finally, we have a data sync here, which writes out the full copy of the data with all the changes that have happened, as well as just the deltas alone, which we use for pushing out to the respective databases. So one of the problems that we had initially was actually around really large graphs. We started with Flink 1.2, and multi-datasets actually ingest independently but get committed together, right? So originally what we did was we actually put the graphs, all the DAGs into a single graph. And so then we actually had trouble when we were sending the graph over to Flink. We had to play with the frame sizes in order for that team to serialize. And then we have about 7 operators per dataset at a minimum. And then physical partitions actually become a multiplier on top of this. So if you have, say, 300 datasets committing together, times 7, that's 2,100, and then times extra more if it's partitioned. So what we did instead here was we actually broke each of these into smaller into subgraphs, and then we put this into its own thread to then submit as multiple jobs into the overall bigger Flink job. What this offered us was actually smaller retry steps. So basically, if one of these failed, then it doesn't affect the whole job. Part of the reason why we did this, if any of you have had experience with Flink, is that if we lost a task manager in the previous way, then we would have to reflow the whole graph. And so if we lost a task manager here, we'd only have to reflow part of the graph. The next thing we really had to do was around serialization. Right, so Flink naturally supports primitive types, tuples, pojos, and rows. So when we have dynamically generated jobs, right, and schema as metadata, so what then do we use, right? So tuples have a limitation of 25 fields, and none of them, it doesn't support nulls. And then over 50% of our data sets are actually wider than 25 columns, and I bet you all of them have nullable fields. So then, in addition to that, some are as wide as 1,000 columns, so it made also using things like rows a little bit difficult. Beyond that, we also have schemas changing all the time. So for us to pre-generate pojos off of the Abro schemas that we have is rather difficult. You can think of it as the analogy between having code in a repo somewhere that we run versus a description of code that we compile the code at runtime and then stitch it all together. And so what we then had to do was actually, it falls back to the Cairo serializer. And we found that the Cairo serializer was actually reinflating the schemas for each record. So what we did was actually made a generic record Cairo serializer where we effectively cached the schemas that we had for each of the records using consistent fingerprint. And we keyed the schemas to that consistent fingerprint, and we're able to improve serialization of the data. Some of the next things that we hit was basically around code group being expensive for us, right? So for those of you who've used code group tends to like having similar sizes on both sides. We had a lot of incremental feeds that may have something in the order of like 10,000 records, whereas the previous batch's data had about 100 million records. And so what happens here is that code group is dominated by the 100 million because it can't start until it's read all the records. And so what we tried to do was actually do something smarter. But before we get into that, you may ask why we use code group in the first place. So I wanted to demonstrate kind of what we're doing in our milestone logic, right? So take a data set that represents a set of customers and when they became a customer, right? So let's say in batch 1, we have me, Regina Chan, and I became a customer on January 1st. So the first batch is easy. You have an insert of me, and the batch it came in is batch 1, and it represents 999 is the view of batch infinity, meaning it's live. And then the time in which this is true for is then into date infinity. And then so let's say in batch 2, we have another customer coming in named Luke Skywalker, and he joined in March 1st. So that's another easy operation. You basically just insert Luke Skywalker in batch 2 into batch infinity, and then that was March 1st into December 31st. So from there, we have batch 3, and let's say I wanted to change my name officially from Regina to Gina on April 1st. So what we then do is mark out this particular original record that represented January 1st to December 31st, and then kind of come in generating from batch 3 until infinity is this idea of January 1st to April 1st was when I was known as Regina Chan. And then going from April 1st until infinity, I'm known as Gina Chan. When in batch 4, we want to say, let's remove Luke, because Luke decided to no longer be a customer coming in June 1st. What we then do is then just kind of mark out this particular record as it came out of batch 4. And then here, coming in March 1st to June 1st, we have 4 to infinity. So if you can think about what we're doing here is that we're actually grouping by keys and creating almost like a linked list and defining what windows have then come across, that we've seen across. And so incoming records can be 0, 1 or more, and then outgoing records could be 1 or more. So what we did with CodeGroup was then kind of use Bloom filters to reduce the amount of records eligible for CodeGroup in the first place. So by using a Bloom filter, we filtered out the previous data and then tried to see whether it's live, and then in the Bloom filter. And then we got roughly about 10K on both sides. Obviously, Bloom filters have a bit of a false positive, so this reduced the amount of that actually gets held up around here, and then we write that into the milestone data. And then what we originally did was actually have another line going straight out of here, representing a no into the milestone data. But we found that because of this kind of line coming out here stops chaining. We found it actually more efficient to reread the data out here and just kind of filter and go straight out here. So I just want to touch briefly about Bloom filter performance. This is an example of Bloom filters sized out of 4 million objects with a 1 in 10,000 false positive rate. As you can see here, it only takes about 9 megabytes or so. And the degradation of a Bloom filter doesn't kind of drop off immediately. As a whole, we have about 500, on average, 500,000 records coming in with a standard deviation of 5 million. So for the most part, this Bloom filter works pretty well as a way of limiting what goes into CodeGroup itself. So with that, I wanted to go into what we did in terms of tuning and cluster management, right? Some of the things that we have challenges around is that we actually don't know, we can't tune in advance because we don't know what data is coming into us. There's a lot of different patterns. Data could be increasing in size over some amount of time. Maybe it's there's more and more data coming in towards the end of the day. There's more and more data potentially coming in at the end of the month. Maybe it's end of the year. There's also scenarios where people have to refeed, say, the last 10 years worth of data because there's something wrong with it, right? And so we don't know in advance what exactly is coming, but all we can do is actually make best guesses. In addition to that, we also have data-specific properties, right? We have the wide data sets, some being 1,000 columns big, as well as wide columns being large multi-megabyte JSON blobs. ultimately, what we want to do is that because we're a multi-tenant cluster, we want to be able to cap resources so that no one data set can cannibalize the whole cluster. And so we kind of have this containers type style capping that we've done. When we first started using this, we used Flink 1.2, and since then Flip 6 has kind of changed our resource utilization as well. Our ingest jobs typically run a single parallelism in our ingest side, mostly because we don't want to DOS their databases by doing multiple connections to it. And so if a particular data set is ingesting slowly, well, what would have happened in the legacy mode was that if something was particularly large, right, we would be holding on to all the resources, even though we're only using one parallelism at the beginning. Similarly, long tails, there's occasionally where certain task managers are responding a little bit more slowly, and we're then also holding on to all the resources until that particular task manager is done as well. So Flip 6 offered us a lot better resource utilization because of the long heads and tails to something where we are able to request individual slots as well as release them as we're done, at a slight cost of a little bit more latency in this request and release in the middle. So what we did was actually just kind of have basic heuristics that we had for each of the data sets. Because we have 90,000 data sets, what we want to do is ensure most of these 90,000 data sets actually run for the most part, right? We aren't always getting the most optimal Flink job run, but that's okay. We don't want to create the noise for our own support teams, nor for our own engineering teams. So for the most part, we use a basic heuristic. And just to give you an idea of the plant that we run on, we have about 500 boxes, each with 24 physical cores and 256 gigabytes. And so what we do is that we actually have a default setting to 2 slots and about 6 gigs per slot. And then we tune the number of task managers based off of the size of the data sets itself. And then from there, what we do is that we calculate the max parallelism for each data set inside the multi-data set cases based off of the number of input splits. From there, there's always going to be dynamically tunable jobs. So what we do is that there are particular jobs that are wider or have particularly big columns. So what we do is that we tune memory sizes for both task managers and job managers. We tune the job managers typically when there's a lot of different keys. Unique keys that we then have to kind of accumulate state over, and then task managers are really particularly around the wide data sets itself that each of the task managers have to process. In addition to this, we have override levels for each of these particular settings, so that even if our heuristics aren't good enough, there's ways to tune them by hand. So with that, I wanted to give you some kind of performance examples. I have different varying sizes. So if you take a look at the first row, what we have is about 2,000 incoming records going into about 270 records with a parallelism of 2, and that finished in 4 seconds. Then we have something a little bit bigger where we tuned it to parallelism of 5, where we have 2 million records going into about almost 1 million of those. And that with parallelism of 5, we ran it into 2 seconds. And then coming into the middle section, we have a bit of a medium-sized data set where the top one is about 18,000 records going into 25 million. And then with the parallelism of 33, that ran in 1 minute and 15 seconds. One thing to note here is basically the the staging size in Avro. So for the second row of the small data sets, you can see that's 250 megabytes going to 85 megabytes, and that's because of the compression ratios between Avro and Parquet. So Parquet is a lot more compressed. So basically, in the medium-sized records, you can see small going to much larger, and then finally the larger going to large, having similar size comparisons, right? About 37 gigs going to 17 gigs is actually about 33 parallelism as well. It took about 3 minutes and 3 seconds. And then on the bottom two, what we have here is actually the record data sets that are of the billion size shape. And so what we have is 25 gigs representing 227 million records going to a compressed Parquet size of 189 gigabytes running on 66 parallelism and about 2 minutes and 41 seconds. And finally, something that's capped at the 300 gigabytes running 100 parallelism, mostly because we capped it at that size, taking longer. And so really the parallelism is driven by the size of the previous batches. And this one will just take 16 minutes and 50 seconds. So I wanted to kind of just give you a comparison of what we had before versus what we had now with Flink. On the bottom side, it really represents each of the data sets that we had. I took out the names of the data sets. On the left-hand side, it represents the amount of time. And you can see the classic in the blue and what we've implemented with Flink in red. And the green bars really represent the amount in percent improvement. And if you were to just kind of draw a linear line across this, it's about 80%, meaning it's a 3 to 5x performance improvement once we've pushed out Flink. And with that, I'll just end our talk here and then take questions.
Could you please a little more precisely lay that out in terms of what is Flink job or what are these other jobs?
Sure. I'll just kind of go back to this. Do you mean the large job graph, or do you mean?
You mentioned that you split this up exactly runs.
Like split this up into here, right? So these are actually all Flink jobs. So what we basically did was we made a whole bunch of threads for each per data set. And so each thread gets its own execution environment, right, which then submits to the same overall bigger Flink job. And so effectively, like we have for each discrete job that we actually have to run, it basically gets its own execution environment in that way. So what we then do is that we're able to gather all the accumulators that are coming out of this. We gather all the metrics and all the other things that for a particular job. And then we kind of manage it within our own application and then push back the final state over to our main metadata service.
Can you tell more about use cases where you use Flink at your bank?
Sure. I mean, this whole thing is kind of being powered by Flink at this point, right? So we're dynamically constructing these Flink jobs, representing each of the metadata that we see to ingest the data itself and to perform a main milestoning algorithm. We also use Flink to do our replication, particularly around. So we used to copy data from the full files from the main cluster to the backup cluster. So what we then do is that instead of copying over that, we were using about 80% of the firm's network bandwidth. And so what we then implemented was we already had the deltas already. So we used Flink also to kind of process the deltas and apply a delta-based merge in our replication. So everything from the data lake itself, meaning connecting to source, validating data to our main milestoning algorithm, to bring data into the lake, to the replication processes. And in addition to that, there's actually a lot of other use cases for Flink at Goldman Sachs beyond the data lake. So people are looking to use Flink for processing kind of transactions, incoming transactions, and developing a state for, as people make credit card transactions or to make transactions between banks or between companies, right? To manage like what is my whole end-all state of the world versus what has actually been processed and been executed. This is how we use it, and people can actually write Flink refiners, meaning Flink transforms, that you then give us a jar for, and we'll run in our cluster as well. Yeah.
And what backend do you use for running these jobs, and how it fits into?
So the question is around having a multi-data center environment. We actually have particularly a primary cluster and a backup cluster, but it's really one big Hadoop cluster that we run this on top of. It has the compute as well as the data, and then we submit these jobs into Yarn, which then handles a lot of the scheduling, and we pretty much kind of have processes that coordinate the replication process between both clusters and keep it in sync. But for the most part, Yarn handles our scheduling and our resource management from that perspective. Yeah.
Cool, thank you. We're running out of time, but maybe you're available for questions outside if people have any more questions.
Definitely.
Cool, so thank you again.
Great.